Let us get started with this following video. Okay, look here. This is related to a person who is descending on a parachute. Okay, again, this is animation, but this works for the real, for the person who, for the real life as well. Okay, now look here.
Did you ever wonder how a parachute works? Here we are about 10,000.
Okay, so this is an animation of if a person falls from an aircraft and if he uses his parachute. So what are the different kinds of forces that will be acting on him, and how come that he happens to land on earth safely and gently? So therefore this 2 minutes video will give you about that idea. Okay, mainly about air resistance. That is very important. Okay, that's a core part of the topic that we are going to deal today. Okay,
1,000 feet up in the air, ready to take one giant leap for science. 1, 2, 3.
someone wants to join.
And right now we're really falling fast. In fact, here we are about 10,000 feet up in how a parachute works. Here we are about 10,000 feet up in the air, ready to take one giant leap for science. 1, 2, 3, and right now we're really falling fast. In fact, at about 100 miles per hour, you could say we're plummeting. The reason why we're falling so fast is the Earth's gravity has a hold on us, and it's pulling us down. In our position, the best way to counteract the effects of gravity is to pull the ripcord on your parachute. See, as the parachute above us expands, it catches air, and the force of that air pushing against our parachute creates a lot of air resistance. As you can feel, the air resistance is really strong, so much so that it equals the pull of gravity, and the two cancel each other out. We're still heading to Earth, but instead of plunging downward at 100 miles per hour, we're softly floating through the sky at a speed of around 10 miles per hour. So even though we jumped at 10,000 feet, thanks to air resistance, our landing feels more like we jumped off a 4-foot wall. Thanks for diving into air resistance and gravitational pull with us today. This has been presented by Bayer Corporation's National Science Education.
Okay, I think all of you got an idea about how a person who is falling down. I think all of you got an idea about how if a person falls down with the help of a parachute, he can land very safely. Okay, what does that mean? First, let us analyze that scenario. Someone wants to join? Okay, so look here. Now, look here, if the person is falling down, okay, if a person is falling down, look here, a person, so can you see here? Yeah, can you see here? A person is falling down, therefore, what is the force acting on him? So if the person is falling down, the force acting on him is equal to mg. Okay, so what does that mean? What does that mean is the person's velocity will change by 9.8 meters per second. Okay, so he gets accelerated. Now look here, can you see here? Two arrows are indicated upwards. One is this white arrow and the other one is this. What does that mean? So if the person is falling down, you see that the air molecules or the atmosphere is going to offer an opposing force in the upward direction. Correct? So because of that, what happens? This balloon is going to glide up and down. Okay, once again I'll repeat. So there are two kinds of forces that are acting when a person is falling in our atmosphere. One, why does he fall down? He falls down because of the weight or because of the gravitational force. So apart from the gravitational force that is acting downwards, there are force exerted by the atmosphere which is acting upwards. Okay, therefore as the person descends, what happens? A stage will be reached where the weight acting downwards will be equal to the force exerted by the atmosphere on him in the upward direction. Okay, we say that the weight will be equal to viscous force and so on. Okay, once again, so therefore if the person is falling down, two kinds of forces will act in the upward direction. So I mean, in an upward direction, a force will act, which is going to, what is that? That you call it as the pressure exerted by the atmosphere on the falling person, which will be in the upward direction. Okay, and this is given by several names. Okay, you call it as viscous force, you call it as damping force, you call it as the resistive force or opposing force or dissipative force, all one and same. Okay, all also they are given by different names. What does that mean? The pressure exerted by the atmosphere is going to be in the direction opposite to the direction of motion. So therefore, so today what we are going to study? Today we are going to study the theory of damped harmonic oscillator. Okay, so before I proceed further, does someone know, can someone define what is damping? What is damping? What is damping?
The reduction of the amplitude of an oscillation over time.
Yeah, once again repeat, Pa.
The reduction in the amplitude of an oscillation over time.
Yes, precisely. Okay, what do we mean by damping? Damping means, so as time lapses, the amplitude of the vibrating body will reduce and eventually it will come to rest. Okay, what does that mean? Look here, simple. So in the earlier class, when we discussed about the theory of free oscillations, what did we do was, we considered, look here, we considered what? We considered the, I'll take a red color brush. Yeah. So in the earlier class, what did we do? We considered the body which was attached to a spring and it was vibrating up and down when it was displaced from its mean position. Correct? Now imagine that this whole thing is happening. So instead of this vibration, if the body, instead of that being set into vibration in air, suppose it is being set into vibration in water. Can you see here? It is set into vibration in water. Okay. For example, if this is placed, for example, if this spring is placed, so this is the wall, the vibrating body is immersed inside a bucket or a container containing water, then what happens? If this object executes up and down motion, what will happen? So there will be force exerted, opposing force exerted by water. Correct? Am I right? Yes or no? Water will exert an opposing force, right? So therefore, today what we are going to do? Today what we are going to study is, if this object, if the object is set into motion in water medium, okay, where? Yeah. So if the object is set into motion in water medium, we are going to see what is the, how does the amplitude vary with the time, or how does the position of the object vary with the time. Okay. So therefore what happens, look here, once again I'll define what is damping means. The case of damped oscillation, because of the frictional force or because of the opposing force offered by the medium on the vibrating object, so the amplitude of the object is going to reduce with the time. So this, how the amplitude reduces with time, this phenomenon or this property, we call it as what? Damped oscillation. Okay, can you see in this graph? Can you see in this graph here? For example, look here. Can you see? I'm drawing a red color line. Can you see here? This red color line shows that the amplitude is decreasing with the time. Eventually, the amplitude approaches zero. Okay, can you see here? Once again, I'll show. Look here. So the amplitude of the object. What do you mean by amplitude? Amplitude is the maximum displacement. Okay, so can you see here that the amplitude will decrease from pulse to pulse, from wave to wave. The amplitude is decreasing. So therefore, what do you mean by damped? What do you mean by damping? If the amplitude decreases with the time when the body is set into vibration, then that kind of oscillation we call it as what? Damped harmonic oscillator. And why does this occur? This occurs because the body is set into vibration in a different medium other than air. Okay, is this concept clear? Okay, can you see here? All of you see here? What is that? The body is set into vibration in a liquid medium. So if it is water, water is going to offer opposing force. If it happens to be inside, say, petrol, the medium happens to be petrol, then the petrol is going to offer a different value of opposing force. If it happens to be oil or seawater, so the amount of force, that is the opposing force offered by the medium on this vibrating body, that will depend on the nature of the medium. That depends on the nature of the medium. Okay, this is clear. Once again, let us recollect the person who is falling from a parachute. Look here, if the person is falling down, I'll use, say, red color. Okay, if the person is falling down, because of acceleration due to gravity. So two kinds of forces will be exerted. I mean, the air will exert a force in the opposite direction. In what direction? In the upward direction. Can you see? It is shown by white arrow mark. Okay, so it is shown by a white arrow mark. So therefore, if the body is set into vibration in a dissipative or in a medium which offer resistance, we are going to see how the position of the object depend on time. Okay, this is clear. Therefore, how we are going to approach, I think this is, I don't require this figure anymore. I will close this. So this is clear. So that is what I have indicated here, that the whole thing is happening in a water medium. Okay, undo it. Okay, I think we will move on. So for this, what is the approach? Okay, look here, this is going to be highly mathematical. Therefore, I will try to illustrate as far as possible by working out either in Paint or by typing them in my Word file. Okay, now this part is done. Okay, now look here, what is the strategy? The strategy. So whenever you do anything, always do things in a very planned way. Okay, don't do things in an ad hoc way. Okay, so what is the strategy? For example, okay, so how are we going to approach this problem? So how do we study the theory of damped harmonic oscillator? So the approach or the strategy or the method or the algorithm, the flow chart is the following. What is that? Step 1, we will draw the figure. Then we will set the body into vibration. Then you are going to find in step 2, you will find what is the resultant force that is acting on the body. Next, in step 3, what you are going to do? You will apply Newton's second law of motion for the resultant force, and you are going to get a basic differential equation in terms of acceleration. And if you solve that differential equation, I will get how x varies with the time. Based on this information, lot of things could be analyzed. Okay, I think someone wants to join. Okay, clear? Okay, so what is step 1? Step 1 is what? Draw the figure, correct? So therefore, let us look at the figure that I have drawn. Okay, now look here. Let me go to the PDF file. Okay, yes. Okay, now is it visible? Look here, this is the figure I am considering. What is that? This is the figure. Okay, let me extract it. Let me extract this. Copy. Let me close all my Paint. Don't require this. Okay, look here, understand point by point. Okay, so what I'm doing now is, okay, is it visible now? Is it visible for you all? Okay, look here, this is the figure. Yeah, Okay, so the body is attached, the body of mass m is attached to a spring of spring constant k. Okay, that's a figure. What is step 1? Draw the figure. Now look here, what we are doing. So I am considering a body of mass m performing oscillations in a resistive medium. Okay, in a resistive medium means what? This whole thing, the whole of this. Okay, all these vibrations are happening where? All these vibrations are happening in a water medium. Okay, for example, consider that this whole of this observation, the whole of this is happening inside a jug or a bucket containing water. Okay, for example, look here, you take a physical balance and if you dip it in water, okay, so it will show a reduction in weight. We call it as buoyancy. Okay, here what you are doing, here the body is set into vibration in water medium. Okay, clear? This is fine. Next, so a body of mass m attached to a spring is set into vibration where? In a resistive medium. Resistive medium means in water. Okay, this is the bucket containing water. Okay, and that is where it is. Okay, this is the bucket containing water. Next, what happens if the body is set into vibration? The amplitude of the vibrating object is damped. Damped means what? It reduces with the time. Why does that happen? That happens because of the resistance force offered by the medium. This is clear. What does that mean? If the body vibrates, look here, if the body is displaced in the downward direction, the water is going to exert opposing force in the upward direction. Okay, right? Next. So what is step 1? Draw the figure. That is done. So now look here. So what is the action I'm doing on this vibrating system? So what is step 2? Step 2 is find the resultant force. Correct? This is step 2. What is step 2? Step 2 is find the resultant force. Can you see here? Therefore, let us find what is the resultant force. Look here. So there are two kinds of force that is acting on the vibrating system. As usual, same thing. What is that? This is the object. This has been displaced. This is O is the position of equilibrium, and it has been displaced in the downward direction to the point B such that OB is equal to X. Okay. What is the resultant force acting on the system? The resultant force acting on the system is given by restoring force of the spring and the resistive force of the medium. What does that mean? Look here. Okay, look here. Let me illustrate here. All of you can see this. Okay, I don't want unnecessary things. I'll eliminate all them. Okay, now look here. So can you see here? What is O? O is the position of equilibrium. Then the body is pulled in the downward direction. Body is pulled in the downward direction to the point B such that OB is equal to X. So X is a function of T. If the body is pulled down, it is going to vibrate up and down in the resistive medium or in water medium. Okay. So O is the position of equilibrium. From O, the body has been displaced to a point B such that B happens to be the instantaneous displacement, and that is going to be X. What is OB? OB is equal to X. This is clear. Now look here. Now look here. I want to talk about the resultant force. Look here. In what direction is the body pulled? The body is pulled in the downward direction. So after pulling it, I will leave it. So if I leave it, what happens? There will be, does the body go up? Am I right? Will the body go up? Because the spring is going to get compressed. Therefore, now two kinds of force will act on the body. Which are those? One is this restoring force. Other is going to be the resistive force offered by water. So what are the two forces that are acting on the body? The two forces that are acting on the body are, one is the resistive force and the other is the restoring force. So resisting force and restoring force both are acting in what direction? Both are acting in the upward direction. Okay, both of them are acting in the upward direction. Can you see here? Therefore, what is the resultant force acting on this vibrating system given by the resultant force acting on the vibrating system? So what is that given by? What is the resultant force given by? Resultant force is the sum of these two components. Okay, it's the sum of these two components. Which are those? One is, look here, can you see here? One is the restoring force offered by the spring. Other is the resistive force offered by water. Okay, clear? No? Simple. What is that? If the person has jumped from the aeroplane, he is falling down, the breeze are acting upwards. That's all. Okay. Now, what is the resultant force? This is clear. All of you are with me? All the students are with me so far? All the students are with me?
Yes.
Okay. So, you're able to understand, right? Okay. Now, let's move on. Next. Look here. Next what we want to know. We want to know what is restoring force of the spring given by, and then we want to know what is the resistive force of the medium given by. So what is that? Look here. Restoring force of the spring as per Hooke's law. What is that? It is equal to minus kx. Correct? No? Right? Next. So what is restoring force as per Hooke's law? It is minus kx. That is this term. Next, what is the resistive force offered by water? Resistive force offered by water is given by minus r into dx by dt. Okay, what does this mean? Okay, why it is called as r into dx by dt? This constant r, we call it as the damping coefficient, and this damping coefficient is going to be different for different mediums. For water, it may be 2. For petrol, it may be 3. And for seawater, it may be 10. So therefore, what is the resultant force now given by? Look here. The resultant force is now given by. What is the resultant force is now given by resultant force is now given by okay, resultant force is given by minus kx for restoring force, and for resistance offered by the medium, it is given by minus r into dx by dt. What is r? R is a constant which we call it as damping coefficient. Now, what is dx by dt? Is it velocity or displacement? What is dx by dt? What is this dx by dt? Velocity or displacement? Velocity, right? So why is it that the restoring force is proportional to velocity? Okay, can you see here? Resistive force is given by minus r into dx by dt. So why is this? Okay, now let me come back to the following. Now look here, all people, can you see me?
Yes, sir.
Okay. So all of you have traveled. So in the last class, I was talking about people having traveled in a train, correct? In the earlier class. Today, I'm interested to ask, have you people traveled in bus? Have you people traveled
Yes,
in
sir.
bus? Yes, no?
Yes, sir.
Right? Yes or no? Do people have traveled in bus?
Yes, sir.
Yes. Okay. Now look here, when you are traveling in bus, many of us may like window seats, correct? Many of us will be liking window seat. So now look here, you sat inside a bus, you are near a window seat, and you have opened the window. Why do you open the window? You open the window so that fresh air is going to come, correct? No? Am I right? That's one of the important things. So therefore, now observe that if the bus moves slowly, the amount of breeze that enters, or the force with which the breeze will enter, is going to be very small. Very small. Okay. On the other hand, if the bus is moving at a very high speed, for example, say 60 km per hour, So if the bus is moving at a very high speed, the force with which the breeze is going to enter the bus is going to be high. You got my point? Is it clear? So the breeze that enters the bus is nothing but what? Opposing force. Okay, and the breeze, the force with which the breeze is going to enter the bus, that depends on the speed of the bus. Okay, therefore, what is this clear to you all? If the bus moves slowly, less air will enter. If the bus moves at a high speed, more air or air will rush with a larger force. Correct? So therefore, can you see here? Okay, let me come back. Yes, can you see here? So what is the resistive force given by? Resistive force offered by the medium will be proportional to the speed of the bus or speed of the vibrating body. So therefore, that will be proportional to velocity. Velocity means dx by dt. So therefore, that will be equal to what? Minus r into dx by dt. So what is this? R is nothing but the constant of proportionality for a given medium. For water, it will be some value. For petrol, it will be some other value. For seawater, it may be some other value. So it depends. Okay, this is clear. So therefore, what is step 2? Step 2 is find the resultant force. That's done. What is resultant force? Sum of this plus this. Resistive force and restoring force. That is given by equation 1. Next. Now look here. So what is R? R is called as the damping coefficient of the medium. R is called the damping coefficient of the medium. Okay, R is called the damping coefficient of the medium. So that depends on one medium to another medium. Now what is step 3? Apply Newton's second law of motion for the resultant force. Okay, where is step 3? What is step 3? Step 3 of our algorithm. The step 3 of our algorithm is apply Newton's second law of motion for the resultant force and then arrive at a basic differential equation in terms of acceleration. Okay, what does that mean? Okay, I will bring this. Okay, people can see now. Yes. Okay, can you see here? Look here, by Newton's second law of motion, what is resultant force given by? Resultant force is given by mass into acceleration. By Newton's second law, resultant force is given by mass into acceleration. So therefore, if I put it in this frame, okay, if I put it in this frame, can you see here? This is this. So what is step 1? All things are done. This is resultant force. By Newton's second law, what is the resultant force given by? By Newton's second law, the resultant force is given by mass into acceleration, which is here. This is clear. Next, what we do? Substitute this value of resultant force in equation 1. Okay. So what is the next step? Next step is, what is the next line? From equation 2, equation 1 can be written as. Okay, what does that mean? Look here. Can you see here? Can you see here? This is equation 1. This is equation 2. This is equation 2. Okay, so all I have to do is, if I use a different color, for example, green. Okay, all I have to do is replace resultant force by acceleration into mass, m into d square x by d of t square. Okay, if you do that, okay, yeah, if you put this value, what you're going to get? I'm going to get the third equation. Okay, therefore, what is the equation given by? The equation, so from equation 2, equation 1 can be written as, so what is that going to be? This, that is m into d square x by d of t square. This is equal to minus r into dx by dt minus kx. This is clear to you all? That's all. In the resultant force, apply Newton's second law and substitute, then you are going to get this differential equation. What is that given by? mass into acceleration is equal to restoring force, and it's a sum of restoring force and damping force. That's all. Okay. Now look here. I think I can take this. Now what I will do. Okay. Look here. So I don't require anything else. So I will undo all the other stuffs. Okay. So this is the equation I got. Okay. Next, what we will do, divide throughout by mass. So if you divide by m throughout, if you divide throughout by m, what you are going to do, what we are going to get. Before that, look here. If I take this equation, if I take this equation, if I shift all these terms on the right hand side, what you are going to get? What we are going to get is, look here, this will become minus r. Sorry, if I am shifting on the other side, that is going to become what? Plus r into dx by dt. This is going to be plus kx, correct? That will give rise to this equation for me. Okay. So if I shift all the terms on the left side, then minus r into dx by dt, that is going to be plus r into dx by dt, and this minus kx is going to become plus kx. Okay. That is going to become minus kx is going to become plus kx. That is what is this equation is. Okay. This equation. Clear? Next, look here. Okay. That's next what we will do. So divide if you divide force by mass, what are you going to get? Acceleration. Correct? So therefore, look here. Divide by m. If I divide this by m, what I'm going to get? If I divide it by m, I'm going to get this equation. Okay, can you see here? If I divide it by m, if I use say orange color, okay. If I divide it by m, I'll use red. Yeah. If I divide it by m, can you see here? This is going to be what? R by m. There will be k by m. Correct? So that's what precisely happens here. Okay. Yeah. Can you see here? So you're going to get r by m into dx by dt and k by m into dx by dt. This completes step 3. What is step 3? Apply Newton's second law of motion and get a basic differential equation in terms of acceleration for the resultant force. Okay. So this is equation 3. Okay. This is equation 3. Next, what we are going to do? What is step 4? Solve that equation and find x of t. Okay. So therefore, how do we solve it? That requires lot of effort. Before that, what we will do is we'll introduce two new terms, which we call it as omega and r by m. Okay. So what are the two new terms? The two new terms we are going to extract are omega square and r by m. Okay. Now look here. I think I don't want other things. Let me take this. Copy. Okay. Look here. I got this. Look here. What is this? This is equation 3. Okay. Equation 3 is what I have written here. Pasted in the paint. Okay. In this frame. Now look here. What we are now going to do. So we will introduce two new constants, namely omega square and r by m. Okay. So what is that? Look here. I will introduce two constants. Omega square. I'll introduce two constants. What is omega square? Omega square is natural frequency of vibration. So that is by Hooke's law is given by what? That is what we discussed in the theory of free oscillation. What is that given by? Omega square is equal to k by m, which I call it as equation 4. Next, you have this constant r by m. No, r by m, I will call it as what? 2b. R by m, I'll call it as 2b. Okay, now look here. What is diameter? Diameter is the longest. What is diameter? Diameter is the longest length of a chord in a circle. So what is diameter by 2? Diameter by 2 will give you radius. Therefore, what is this B? B we call it as semi-damping coefficient. Okay, what is B? B is half of something, just like radius is half of diameter. B is half of something. Therefore, B is called as semi-damping coefficient per unit mass. Don't worry, this B is somewhere related to damping coefficient, which is R. That's all. Okay, so if I introduce two new variables, omega square and 2B, then this equation 3 can be written as what? Look here. Here it's going to be 2B. This term is going to be omega square. Okay, so therefore what do you see? From equation 4 and 5, equation 3 can be written as, okay, I will copy this. From equation 4 and 5, equation 3 can be written as. What does that mean? Look here. Look here. From equation 4 and 5, equation 3 can be written as. Can you see here? Okay, from equation 4. Equation 4 is this. What is equation 4? Equation 4 is this. This is equation 4. What is equation 4? Omega square equal to K by M. What is equation 5? R by M equal to 2B. Therefore, look here. This term is going to be 2B and this term is going to be omega square. That is what precisely you got here. Okay, that's what precisely we got here. Okay, therefore, so from equation 4 and 5, equation 3 can be written as, like this, and this I will call it as equation 6. Therefore, what is equation 6? Equation 6 is given by acceleration plus 2b into dx by dt plus omega square x equal to 0, which I will call it as equation 6. Okay, that's precisely is what written here. Okay, can you see here? So d square x by d of t square plus 2b into velocity plus omega square into displacement equal to 0 is called as equation 6. Okay, now what is the goal? Goal is to solve this equation. So if I solve this equation, eventually we are going to get a big expression like this. Okay, a big expression like this, which is equation 10. So we will approach things in a very systematic and in a very simple way, in one step at a time. Okay, now look here. See, can you see in this graph? The first graph I wrote, no? There. Can you see here? This was my first graph. Correct? No? Amplitude is decreasing. Okay. The amplitude roughly decreases like this. Okay. This red color curve is nothing but it's an exponentially decaying function. Exponentially decaying function. Okay. Can you see here? You see in my figure? The red color curve shows what? An exponentially decaying curve. Okay, so therefore the solution of this differential equation, 6 is going to be of the form, the solution of equation 6 is going to be of the form x of t is equal to a into an exponential function, a into e power alpha t, where a and alpha are two new constants that can be determined based on some initial conditions. Okay, this is clear for that. So are people with me? People are with me?
Yes, sir.
Sir.
It's very mathematical, no? It's nothing. You read my notes using the handset, then you write it as you read, you write it on a sheet of paper, you will understand very nicely. Okay, is it clear? So now shall we move on to the solution, finding the solution of this problem? Yes, shall we do?
Yes, sir.
Yes, sir.
Okay, look here. Anyway, Corona has come. Now we have to acknowledge the problem and get vaccinated and face it. Correct? No? Right? So therefore, now what we will do? Now we will try to find the solution to our problem. Okay? So therefore, look here. Now we will move on, pa. Okay? Okay, this figure I don't require now. Don't require. Let me go to this. Okay, so people are able to understand now. Lot of so nice things. Okay, my child also will put lot of scratch. Can you see now? Okay, yeah, fine. So I'll just retain only what is required. Okay, pa. Look here. This is equation 6. Done. No need to tell about it. What is the solution given by? Solution is given by x of t is equal to, let the solution of the equation 6 be of the form x of t is equal to a into e power alpha t, which is called as equation 7. Okay. So that, let me put it in this frame. Okay. Look here. Can you see now? This is equation 6. I want to solve and I want to find how x depends on t. I want to find how x depends on t. So as per our experience, how does x depends on the t? So you know the structure of the solution. What is the structure of the solution? Structure of the solution is, it is exponentially, it exponentially depends on time. Okay, right? So therefore, the solution of the problem is as per our proposed structure, as per our known form. What is that? A into e power alpha t. Clear? Now look here. In equation 6, you know what is x as given in equation 7. Okay, next, look here. You know what is dx by dt? You don't know. Therefore, you will find dx by dt by differentiating equation 7. Next, do you know what is d square x by d of t square? We don't know. So that you will find by differentiating this twice with respect to t. Okay, this is clear? Idea?
Yes, sir.
Clear? No? Therefore, that is what we will now look in the next few steps. Okay. So now what you see, solution is given as per our proposed structure. So things are under our control. So I want to find dx by dt and d square x by d of t square. So if you differentiate equation 7 with respect to t, what you are going to get? You are going to get dx by dt will be equal to a into alpha into e power alpha t. And if you differentiate again with respect to time, what is that going to be? It's going to be d square x by d of t square equal to a alpha square e power alpha t. How does this come? Let me show it. Look here. All of you kindly look at kindly watch me. Okay, I will put here. This is equation 8. Let me put all things in one single frame, one single slide. Okay, put it here. Okay, people are able to see. No, this is equation 7. This is equation 6. This is 7. This is equation 8. This is equation 9. Okay, therefore look here. So let me show how I got 8. How I got 8. Okay, let me go to my PDF file. Yeah, I'll go to the end. Okay, look here. What is x? X is equal to capital A into e power alpha t. E power alpha t. e power, I'll write it as ALP into T. Okay, e power alpha T. Is it visible? Let me increase the font size. For example, I make it as 20. Now it's visible, right? Right now. Okay, look here. Let us show it here. What is this? X is equal to A into e power alpha T. What is that? This is equation 7. This is equation 7. Now, if you differentiate equation X with respect to T, you are going to get what? Dx by dt. Dx by dt. What is dx by dt given by? Look here. Here, A is constant. Therefore, let me write A here. Okay. Next, what is d by dt of e power t? It's going to be e power t only. Therefore, it's going to be this entire term. Okay. What is d by dt of e power alpha t? It is e power alpha t only. Next, what you have to do? You have to also differentiate this term, e power alpha t. What is d by dt of alpha t? It is alpha. So, therefore, what you are going to get is a alpha into e power alpha t. Okay, a e power alpha t. That's precisely is this term. Okay, if I copy this and if I paste it here, okay, a alpha e power alpha t, a alpha e power alpha t is equation 8. Clear now? Look here. So go to the paint. Yes. Okay. So what is equation 8? Equation 8 is dx by dt is equal to a alpha into e power alpha t. Now, if you differentiate equation 8 with respect to t, you are going to get d square x by d of t square. Again, what will happen? This alpha is going to come out. Therefore, what is a alpha into alpha? It's going to be a alpha square. That is what you see precisely here. Understood? No? Okay. So, if you differentiate this again with respect to t, I will simply write it. So, if I do this, what happens? D square x. So, that is d square x is acceleration. That will be equal to what? It is going to be so a into alpha square into this term. Okay, that I'll not show it now. So if you work it out, you'll get. Okay, I think the idea is clear. So what is that? So what is that? Look here. Idea is x of t is known as per equation 7. Find dx by dt by differentiating it. That will be equation 8. Find d square x by d of t square. That is going to be equation 9. Now what you do? Put this value of x of t, dx by dt and d square x by dt square. Where you are going to put? You are going to put that in equation 8. Sorry, in equation 6. Okay. That's what my next step of notes is going to tell you. Okay. What is that? From equation 7, 8 and 9, equation 6 can be written as. Equation 6 can be written as. Therefore, look here. I'll just plug it in and plug it and show. Let me take this. Copy. Look here. Let me put it somewhere here. Yeah. Okay. Now look here. Now look here. Use, for example, blue color. Yeah. Can you see here? From equation 7, from equation 8, and from equation 9. Okay. So what is d square x by d of t square? Can you see here? D square x by d of t square is a alpha square e power alpha t. That is precisely is this term. That's precisely is this term. Okay. Next, what is 2b? What is dx by dt? Dx by dt from equation 8 is a alpha into e power alpha t. That is precisely is this term. A alpha e power alpha t, okay, plus omega square into A into e power alpha t. This is clear, all of you? This is clear to you all? This step, okay? Now look here. Now look here. In this, what I can do, I can take A e power alpha t common. Therefore, look here. I will zoom this. I don't want these stuffs, so I'll take a new file. I don't want these stuffs. Now look here. Okay. I'll expand this. Okay. Now can you see? Can you see? I can take I can take, what are the terms that I can take common in each of these? They are A e power alpha t. Okay. A e power alpha t. A e power alpha t. If I take common, what I'm going to get? So what you are going to get is A into e power alpha t. What are the terms that will be inside the bracket? They are going to be alpha square coming from first term. Then you have, look here, 2b alpha. So that is going to be 2b alpha here, 2 alpha b. And in the third term, it's going to be omega square. So that's going to be this. Okay. Therefore, you are going to have A into e power alpha t into this quantity equal to 0. Okay. Don't worry too much. So this means that either x is 0 or this quantity inside the bracket should be 0. For non-trivial solution, what we require? For non-trivial solution, alpha square plus 2 alpha b plus omega square, this should be 0. If I undo all this. Okay. So what I require for non-trivial solution, what should happen? Alpha square plus 2 alpha b plus omega square, this should be equal to 0. And this is a quadratic equation. If you solve it, you are going to get alpha. What is alpha? Alpha is the exponential term. So what is alpha given by after solving this quadratic equation? It is given by alpha is equal to minus b plus or minus square root of b square minus omega square. Okay. How to get this I will show in the next class. Right now, just understand what is that. If I solve this equation, I'm going to get the solution given by alpha is equal to minus b plus or minus b square minus omega square. This is clear. So therefore, look here in equation 7. This is our equation 7. Alpha is known. Therefore, put that value of alpha which you got after solving the differential equation. Look here, alpha has both positive plus square root of something minus square root of something. Therefore, if you substitute this value in equation 7, how does x depend on t? So the nature of how x depends on t is given by equation 10. So what is that? X of t is equal to c into e power something plus d into e power something. Okay, that's the solution. So I don't have to write it here. I think here it is visible. Okay, so where c and d are the constants that can be evaluated using some conditions. So therefore, by looking at equation 10, what are the different types of damping that exist? That we will study in the next class. Understood? I will stop here. Look here, I try to illustrate as far as possible the mathematical concepts as far as possible. This part I didn't show. How you get this, that I will show it in the next class after the end of the discussion. Right now what? Right now is, if I find the resultant force, I'm going to get this basic differential equation, which is equation 6, and my solution has the structure which is exponentially decaying function that is given by equation 7. Then find dx by dt, d square x by d of t square, that is 8 and 9. If you plug in, you're going to get this differential equation. And if you solve this quadratic equation, this is the solution. and that if you plug in equation 10, how x depends on t is given by this big expression. Okay, this big expression. This is clear. So I think I'll stop here. Okay, what is the final expression given by? The final expression is this. And all of you see here, this is the final expression. How x depends on t is given by this expression. Can you see here? Suppose I use a orange color. Can you see here? This is the final expression I'm trying to highlight. Okay, so from equation 10, we can discuss the different types of damping. Okay, so I will stop here. If anyone has any doubts, you can ask. Just follow my notes. It is just good enough. Okay, I will stop here now.